Hi everyone, welcome to Pharma World. This is the seventh part B of the tutorial. Here we will focus on the intravenous pharmacokinetics. You can check the basics of the pharmacokinetics in the earlier part of the series for a better understanding. Let's start. There are a lot to know in the world of pharmacokinetics. We will be dealing here with one compartment model and the PK associated with multiple administration of drugs. I will speak some same slide of the previous part in case you have forgotten. So little recap for a smooth flow. So the first figure shows that of a single IV dose, whereas the second figure tells you about the plasma concentration changes after multiple such doses. The basic idea of multiple injection is to attain the steady-state plasma concentration. Let's recap about steady-state plasma concentration. So steady-state is achieved at a time when, under a given dosage regime, the mass of drug administered or absorbed is equal to the mass of drug eliminated over a dosing interval. That's very important to remember. So apart from a single compartment that I have discussed, other assumptions for the discussion are as follows. First, that it has to follow linear pharmacokinetics. Tissues can take up extremely large amount of drug. The apparent volume of distribution, the elimination half-life, and the elimination rate constant are independent of the number of administered doses. Fourth is the time interval between dosing or successive doses is constant. And the fifth and the important one is the administered dose is equal at each successive time interval. So the objectives of part B, part A we have already discussed. In the part B, we'll discuss about the dose ratio. Second is the concentration of the drug at a given time following the end dose, drug accumulation ratio, and as well as the calculation of the loading and the maintenance dose. So the first one is dose ratio. It is indicated by that R, small r. So R is the dose ratio. It is named after a German scientist actually who developed these equations. Uh, Miss, I will just keep simple. So just try to give you a basic understanding what is exactly the dose ratio. So this ratio helps you to determine the amount or the plasma concentration of a drug in the body at any time t. Okay. So following the administration of any end dose like second dose, third dose, fourth dose, or 7, 8 dose, whatever it is, by any means like intravascular or extravascular routes. So if you want to determine the plasma concentration of a drug after some like 7 to 8 doses, then you need to understand about the dose ratio. So this is the dose ratio where n is the number of administered doses, k is the first order elimination rate constant, and this tau is the dosing interval. So this is all required, all that is being required to determine the plasma concentration of a drug in the body at any time. So next point is about the concept of a drug accumulation in the body, denoted by capital R. The previous thing that is dose ratio that is denoted by small r. So the administration of a drug on a multiple dose regime will result in accumulation of drug in the body that we have understood from the previous lectures. So R simply indicates how high the plasma concentration will be at steady state compared with the first dose of the drug at a comparable time within the dosage regime. So let's understand by an example. For example, if R is equal to 2 here, for a given drug, if it is like 2 microgram per liter from the very first dose, then the steady state plasma concentration will be like max to max, it will go like 4. Okay, 2 into 2 is equivalent to 4. So, so R value of 2, that means that average plasma concentration at steady state will be twice the average plasma concentration for the first dose. So there's some formula. This is the formula you can through which you can easily calculate the R value. Therefore, the knowledge of the R reported R value permits prediction of the peak trough for average plasma concentration at steady state from the knowledge of the maximum, minimum, or average plasma concentration for the first dose. So, if you try to figure out the average plasma concentration of the first dose, you can figure out the average steady state plasma concentration, as well as if you figure out the Cmax following the first dose, you can able to predict the maximum concentration in the steady state plasma concentration. So let us try to understand with an example here. Here the accumulation ratio is 2. So the parameters used is that elimination rate constant. So this is constant for a drug. Okay, the half-life is 24 hours, and also the drug is being given once daily. So with that we have an accumulation of 2. But if we give the dose more frequently, that is every 6 hours, the tau is equal to 6. So in this example, 25% of the one half-life of a drug. So there will be greater accumulation of the drug. So R is equal to 6.25. Okay. However, the point to be noted that if you give these divided doses, the overall accumulation will approximately same, because if we suppose if the total dose in the 24 hours is like 8 milligram, okay, so it will give a concentration of X in after the first dose. So in the case of the first thing that we will get 2x at the steady state plasma concentration. Similarly, now if I divide the dose, this 8 milligram into 4 times daily, it will become 2 milligram. Okay, 2 milligram 4 times daily. So since there is a low dose, and the plasma concentration that will be seen will be like X is equal to 4. Okay. Now, but we see that there is an accumulation of 6.25. Now we have to multiply this 6.25 into X by 4. So what we'll get around 1.6 or 1.77 like this, close to 2. So the crux is that if the total dose administered is kept constant at a given interval, the R, that is the accumulation ratio seen for a drug in a steady state plasma concentration, also remains same. R value may be higher, what you can see for smaller intervals, but the ultimate thing, that is the average steady state plasma concentration, will be same. So next we have a table which shows the relationship between a drug accumulation and a dosing interval. So if the elimination half-life in a dosing interval is equivalent to 1, then the drug accumulation of R value is 2. If it is like 0.25, then it becomes increases, and if the elimination half-life in a dosing interval is like 2 or 3, the accumulation decreases. Okay. Next is another parameter called fluctuation of doses. So if you remember from the last session, if dosing is more frequent, the range of drug concentration is smaller. That is, the difference between the maximum and minimum plasma concentration at a steady state will be smaller. Hence, frequent dosing, that is smaller doses, if practical, is preferred over less frequent larger doses in order to avoid a toxicity problem at a steady state. So here it is an example. For example, if the half-life of the drug is 12 hours and you prescribe the dose at 6-hour interval, the drug fluctuation is less. Okay, so that is very important. So till now we have discussed many times about the loading dose and maintenance dose, why it is very important. A few points you need to consider. First of all, in the intravenous bolus loading dose may be administered to obtain an instant steady state plasma concentration. That is the prime objective. And the calculated loading dose should be such that at time tau after its administration, the plasma concentration of drug is the desired minimum plasma concentration at steady state. So this is the thing, that you have to reach a certain concentration to manifest its effect. So how you can calculate the loading dose? It's simple. Just you need to know the volume of distribution of the drug into concentration steady state for exactly you need, and divide by bioavailability. And similarly, we have a formula for maintenance dose. It is the concentration steady state, just like this one. We have the clearance of the drug, dosing interval, that is very important, and divided by bioavailability. So this is a simple formula which is very helpful to calculate the loading. Next, try to understand the relationship between the ratios of loading dose to maintenance dose, and how it is important to attain the steady state plasma concentration, and along with this relationship to elimination half-life. So from the table, what you can see here is that there is a ratio of loading dose by maintenance dose. So loading dose need to be double here in this case, for example, need to be double to the maintenance dose. If the time period between the loading dose and the maintenance dose is equal to one half-life to reach the steady state plasma concentration. So here in this picture, you can see here that this is, if we go through this maintenance dose, only maintenance dose, no loading dose. So it takes some time in that case. Now, if we give a loading dose, suppose if the half-life of this if the drug is like 6 hours, okay, 6 hours is the half-life of the drug. So the time duration between the loading dose, giving the loading dose, and the maintenance dose is equivalent to the one half-life. Okay, so in that case, the ratios of the loading dose will be like 2 times more to that of maintenance dose, and it will reach the steady state plasma concentration. So what you can see that it reaches the steady state plasma concentration after delivering the loading dose. If we want to make it faster, like within a span of 3 hours, if we want to like reach the steady state plasma concentration, in that case, the loading dose would be like 3.4 times as compared to the maintenance dose. Lastly, I just want to recap again regarding the relationship between the number of doses required to attain a desired fraction of steady-state plasma concentration and the dosing intervals in terms of number of elimination half-life. So if the elimination half-life of a drug is like 24 hours and if you are giving it once daily, okay, then around 95% of the steady-state plasma concentration is obtained by the fourth dose. That is what we generally read in the textbooks, that it takes 4 to 5 half-life to reach the steady-state plasma concentration. That is only if you give the drug within the elimination half-life. That is 24. If the T-half is 24 hours, you give it once daily. If you give like 12 hourly, okay, so in that case, to reach the 95% steady state plasma concentration, you have to give like 8 doses. Similarly, if we give like if the n is equal to 2 or 3, the amount of drug that is being required to reach the 95% will be less as compared to the one that is the standard thing. So these are my references, so please like and share and subscribe my channel if you like the presentation. See you next time. Bye bye.